In this lesson, we're going to go back and revisit moment of inertia, and we're going to introduce the parallel axis theorem. First, just let's go back and revisit moment of inertia. So, as it says here, let's consider a system that has four particles. So 1, 2, 3, 4. I'm not going to label them. They're all the identical m's. And we are going to let this four-particle system be connected by really light massless rods, right? Connecting them together, and we are going to let them rotate. In this example, we're going to assume they are rotating about this axis, which passes through the center of mass of the system. So it's going to swing about this axis like the purple rotation we have here. And if we consider this a point particle system, we calculate the moment of inertia based on the sum of the mr squareds that we have here. We have 4 m's, each at the same r distance, and since we're saying it's 2a apart, each r equals a, so 4ma squared. Now, we're going to see why in a couple of minutes, but for right now, please get this into your notes, and I've exploded it to emphasize it, that the moment of inertia about the axis that goes through the center of mass point will always be the smallest moment of inertia for that system. And this is why, now we can understand why we say that the center of mass point is nature's point of rotation. When you just randomly toss an object into the air, if it is going to rotate, because the inertia for rotation is smallest about the center of mass, it will rotate about the center of mass point. And to show this, at least numerically by example, let's say we move the axis of rotation from the center over here to the left. So we're going to move it from the center to the left and spin this four-particle system about this new axis. Well, our new moment of inertia is still based on the mr squareds, but now we have to be a little careful. So I have labeled them 1, 2, 3, 4, and m1 and m4 have no r, so they are right on the pivot. So no radius of axis of rotation. The r distance, axis for the rotation, is now 2a for particles 2 and 3. So we have m 2a squared, so we get m 4a squared from particle 2, m 4a squared from particle 3, and now notice that the rotational inertia about this axis is 8ma squared, double what we had up here for the moment of inertia around the center of mass. And whether we moved it all the way to the left or just a little bit to the left, even a smidge to the left, it would be greater than 4ma squared. So we always have the smallest moment of inertia about the center of mass point. Now let's introduce our parallel axis theorem. Very important theorem to problem solve moment of inertia problems because it will simplify problems away from a calculus-based calculation and allow us to just utilize this equation, which, by the way, is the parallel axis theorem, to calculate the moments of inertia. So what the parallel axis theorem says is that if we move to a new axis, so this would be the new axis in our last example, and we're going to go back and revisit our last example in a moment. If you move to a new axis, so new axis that is parallel to the center of mass axis, the new axis will be larger than the center of mass axis by this factor, mh squared. And notice it's larger, always larger. Any rotation off the center of mass axis is larger than the rotation through the center of mass axis, the moment of inertia. Best way to see this is by example. So our red ICM, right, from our last example, so we're going back and just revisiting the same problem we just talked about, was the 4ma squared that we had through the center of mass axis. Now we're going to consider our new axis from the last page of notes to be our I parallel. So let's go down here. So now we have I parallel to I center of mass, and we are going to just utilize the parallel axis theorem to get our answer. So we had I center of mass was 4ma squared. Now, using the parallel axis theorem, we are simply going to add this term to I center of mass. Capital M is 4m, and the h squared is always the perpendicular distance between the two axes. So in this case, h is going to equal a. So we replace h with a, and we get the 8ma squared that we got on our last example. Now, for a point particle system, the parallel axis theorem saves us a little time, but really not that much. But let's go, as it says here, to our last page of notes. So go to the last page of notes, the last page of notes, and let's look at two examples of the parallel axis theorem that are quite useful. If we consider a tabulated understanding of the center of mass moments of inertia, like let's do the sphere down here first. So we can go to a table and see, oh, the center of mass for a solid sphere, like the Earth, spinning on its central axis, would be 2/5 mr squared. We would have to use calculus to calculate that, and we will see how to do that in our upcoming lesson. But if we employ the parallel axis theorem, we can now very quickly, within seconds, calculate the new moment of inertia of a spherical system if we pinned an axle to the outer rim of that sphere and then spun the sphere around the new axis. So the center of mass would now be going around that new axis, and if that's what the problem called for, normally we would have to go use calculus, and it's a very complicated calculation, time-consuming, but look what the parallel axis theorem gives us really in seconds. We grab the center of mass answer that is tabulated, the 2/5 mr squared, and we just add our mh squared parallel axis additional inertia term to it. M is the total mass of the sphere, so that remains capital M. R squared in this case is the h squared. It's the parallel distance, the perpendicular distance between the two axes. So we simply take 2/5 mr squared, add mr squared, so 1, so 5 on 5, 7/5 mr squared. Wow, right? We get it really easily. And here, your table actually shows a parallel axis solution. Here, 1/3 ml squared. But we could have, now that we know the parallel axis theorem, just left the table with this term and simply made the parallel axis calculation, adding the additional mh squared term to it to get the 1/3 ml squared. So, very powerful technique. Please make sure you have all the notes from this lesson annotated down, and that you ask questions if you want clarification on anything that was discussed.